In this video, we're going to take a look at some pretty simple concepts related to vectors in Rn. So we're going to focus on our Euclidean vector space. And depending on your background, you may know all of this stuff already. But just for fun, let's go through it. We're going to talk about the idea of length, right? And this interesting product called the dot product. So let's go ahead and set the stage and see what we're going to be working with. So since we're working with vectors in Rn, we know what the general vector in Rn looks like. So let v be equal to, and then I'll just use our standard notation. We'll have v1, v2, and then since I'm leaving the dimension of the vector arbitrary, I'll just have my vector be vn. And going back to when we started talking about vectors, one of the kind of geometric ways you can think about a vector, it's an object that has a length and a direction. So the question is, well, I just wrote down a vector, what would its length be? So we're just going to go through and define some things and then just do some simple examples. Nothing too complicated here at all. But so the length, I can spell length, or norm, it's sometimes called the norm. So the length or norm of V, and this is how it's denoted. Now, again, depending on your background, I might use a notation that you're not familiar with, or maybe you've seen it in a slightly different context. The reason will become clear shortly, if not in this video, in the next video, but we're going to use these two double bars. They look like extra powerful absolute value bars. So this is what we're going to use to indicate the length or norm of a magnitude. Some people, of a vector. Some people even refer to it as the magnitude of a vector. So that norm or length is defined by, and here is the calculation. Pretty simple, and it's based on just the way we compute distances in Euclidean spaces. So there's going to be a square root involved, and all we do is take each component of our vector, no matter how many components we have, square each of them. So basically do that calculation. I'll do my dot, 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 and then that calculation, and then add them together, and then take the square root of that, right? And that's how we compute the length, right? So again, this is a formula that you might recognize. Now, once we have the concept of length, it then allows us to define a special type of vector, which we call a unit vector. So a unit, the word unit, especially in mathematical context, often implies something having to do with the number 1. So a unit vector, right, is pretty simple definition, has length 1. All right, there we go. So yeah, let's just do a little example, and I'll do an example in not the standard like R2 or R3, but let's just go up a little bit on the dimension, but not too crazy. So let's say our V, let's take a vector in R4. So let's say it's 1, -1, 2, 3, right? Then if we want to compute the length, we'll just take the magnitude of that, and here's our calculation. So it's going to be 1 squared plus -1 squared plus 2 squared plus 3 squared. And of course, we got to do our order of operations. We can't forget that good stuff. So it's 1 plus 1 plus 4 plus 9. And if my math is right, I think that's 15 under the square root. So the magnitude is the square root of 15. So again, I picked a vector in R4, not the easiest thing to visualize, but if we could, and if we associate this with some directed line segment, then, and let's say we treat it as a position vector. So in R4, let's say this is the origin in R4, and then for our V, let's say that's our directed line segment. And what we're saying is that now this length is the square root of 15, right? So going from there to there. That's all it is. And the other thing we can note here is that this v is not a unit vector because the square root of 15 is not 1. But suppose we wanted to find a unit vector that acts in the same direction, right, as v. So we don't want it to be this long, but we want to maintain its direction. Now think about our vector operations. So we know in terms of preserving the direction of a vector, right, but not necessarily worried about its length, we could use scalar multiplication. Remember, you know, a scalar multiplication, we can stretch and contract, and we can even change the direction so it's oppositely directed. Well, so here's how you can actually, and I'll give you a little formula, right? But it should make sense. If I were to take the vector v and essentially divide each of its components by the magnitude, right? Another way I could say it, if I were to multiply v by the reciprocal of its magnitude, then I would basically be shrinking it because the square root of 15 is bigger than 1. If I take the reciprocal of the square root of 15, I'll get a scalar that is less than 1. And then, so let's see what that happens. So I'm going to define a new vector. So suppose u is 1 over the square root of 15 times v, right? So if I do this, yeah, so just my basic scalar multiplication. So 1, -1, 2, 3. If I do my multiplication, I'll have this 1 over the square root of 15, -1 over the square root of 15, 2 over the square root of 15, and 3 over the square root of 15. So that's a new vector, but we know just by our properties of scalar multiplication that these two vectors act in the exact same direction, but they clearly can't have the same magnitude, right? It should be pretty clear, right? But let's verify. Let's see. Let's check to see what the norm or length or magnitude of this new vector is. Well, so we got to square each of these components. So we'll have 1 over root 15 squared plus -1 over root 15 squared plus 2 over root 15 squared plus 3 over root 15 squared, and all of that under a big square root. Well, now look at what we're going to have. So if I simplify all those fractions that are being squared, I'll have 1 over 15 plus another 1 over 15 plus a 4 over 15 plus 9 over 15. And then when I do my add my fractions, I end up with a 1. So what we've done by taking a non-zero vector and dividing each of its components by its magnitude, or you could say multiplying v, scaling v by the reciprocal of its magnitude or length or norm, we've created a unit vector. So basically now if I were to go back, so let me go back to my little sketch here. So this obviously is v. So u now, let's say if I make that a position vector as well, would be like this. So that will be my u, but now specially it will have that length will be 1 unit, right? And the process of taking a non-zero vector and turning it into a unit vector is called normalizing that, or some people might say standardizing, right? So in general, just write this down. So in general, if v is a non-zero vector, then the unit vector we could say acting in the same direction of v is, and let's write down that little formula. So let's call it u. And remember what it was? It was the reciprocal of the magnitude. And this is why we needed v to be non-zero, because we don't want a 0 here in our denominator. Don't want that. and then times v. Yeah, so pretty useful formula, and it is in courses that rely a lot on multivariable calculus or calculus-based physics, you normalize vectors all the time. All right, so there we go. So that's the idea of length and then unit vectors, and then once you have this, we can sort of extend the idea. So I'll just give you a couple extra formulas, maybe do a couple examples along the way. So suppose I have these two vectors now. So let's say I have a u and a v. A u is not necessarily a unit vector. We don't know, right? So let's say this is u, this is v. I am trying to find the distance between them, meaning where they both end up. What is the distance here from this terminal point to this terminal point? Now, obviously, what I can do is I can form a vector, right? I can form a vector that goes from one to the other. So if I wanted to go from the terminal point of, in fact, let me do it this way, the terminal point of v to the terminal point of u, that vector, I could just do that head minus tail calculation, right? So let's do this. So let me call this w, which is the vector that goes from v to u. It would just be u minus v, right? And then if I'm trying to find the distance of that red directed line segment, then I could just take the norm of this difference, right? So this implies that the distance between u and v is, so you could just call it d for distance. But it would be, yeah, the magnitude of this new vector, this red vector that I just defined of w, which is this, right? Okay. And the interesting thing about this way we're defining the distance is that there's a lot of important relationships between this and the regular absolute value. It's like when you take the absolute value of let's say a minus b, you're actually just finding the distance between those two, let's say, real numbers on the real number line. That's what it is. And this concept of norm actually allows us to extend that concept of distance to not just something that's one-dimensional, but hey, n-dimensional, which is pretty cool. All right. So there's that. And then the next thing I want to mention is just the dot product. And this seems to like come out of nowhere, but when we defined matrix multiplication and we were talking about row times column, each one of those row times column was really a dot product, right? So for this, we need two vectors. So let u and v be in Rn, and let's define them this way. So again, let's say we'll just have u1, u2, dot, 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 un, and v is v1, v2, dot, 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 vn, right? Well, we can find, so this is how we define the dot product. So think of u as a row, and then think of v as a column, right? I'm just writing them both as rows, but you can think of it this way. So we define the dot product, right? And it's basically just u, and we put a little dot there. Sometimes I make it a little bigger just to emphasize that this is not just regular number multiplication, but it's vector, quote unquote, multiplication. To b, and then this is what, let's write down the formula. So u dot v, and again, think of how we did. You would multiply the corresponding components, right? Row times column, but now I'm just going to take u1 times v1, and then you got to add to that u2 times v2, and then keep doing that until you get to the nth entry. So un vn, right? And that's your dot product. So let's end this video with a quick example of the distance between two vectors and the dot product between two vectors, right? So let's up the dimension even further. So let's say u is let's say a 5-dimensional vector, right? So R5, so like this, like that, and let's say v is equal to, let's say 4, 1, negative 1, 0, 0, something like that, all right? So the distance between u and v, you can write it like this. You could use d, and then in parentheses, you could just do u comma v, right? That's one way to denote the distance. And then, yeah, so this would be so let me write down the formula that I wrote down. So it's the magnitude of u minus v. Now, order of operations is important here. We have to do the vector operation first. So we have to subtract the vectors and then take the norm of the resulting vector. So I'm just going to do the subtraction mentally, pretty easy. 1 minus 4. Again, we're doing that component-wise. 2 minus 1. Negative 1 minus negative 1 is 0. 0 minus 0 is 0. And then 3 minus 0 is 3. So that vector there is u minus v. Oh, gotta switch to my double lines. And then now we use our norm calculation to get the length or the norm of this. So then it would be the square root of negative 4 squared plus 1 squared. I'm not going to write the 0 squared because those are actually, you know what, for fun, let's just write it down so that you're not missing any step at all. And you got the square root of 16 plus 1 plus 9, so that's root 26. So the terminal points, if these vectors have the same initial point, so if they're concurrent, then their terminal points are root 26 units apart, again by this Euclidean measure, right? And then so that's the distance, and then the dot product would just be u dot v. Let's see what we get. So we're going to take, again, I'll write the intermediate steps. So we're multiplying now the corresponding component, so 1 times 4, and then adding to that the next product of corresponding components, so 2 times 1, and then plus negative 1 times negative 1, and then plus 0 times 0 plus 3 times 0. So the last two terms don't contribute anything to the sum. The first three terms do. So we have 4 plus 2 plus 1, and we have a dot product of 7. Now, again, just like with matrix multiplication, initially it's like, well, what does this thing even mean? Well, a natural question is like, what does this dot product even mean? So in the next couple of videos, we're going to talk about the dot product and some other geometric and algebraic properties that are related to this idea of norm and dot product. So I know you are so looking forward to learning more about this. So just jump over to the next video right now. I'll see you there.